radius, and center. Well, thus far, we've been considering power series that are centered around zero. By which I mean, we've been looking at power series that look like this. The sum n goes from 0, say, to infinity of c sub n times just x to the n. But we can center our power series around some other point A. So instead of writing this, let's say I want to write down a power series that's centered around some other point, say A. Well, then I'd write my power series like this. The sum n goes from 0 to infinity of c sub n again, but now times not just x to the n, but x minus a to the nth power. In this case, the interval of convergence is centered around a as well. Well, let's find an interval on which this series converges. And the goal is to show that that interval is really centered around a. So it legitimately makes sense to think of this power series as centered around a. And to find the interval on which this power series converges, I am going to use the ratio test. So let's do that now. So how does the ratio test work here? Well, it asks me to look at the limit as n approaches infinity of the n plus first term, c sub n plus 1 times x minus a to the n plus first power, divided by the nth term, which is c sub n times x minus a to the n. And I've got absolute value bars here because I'm really applying the ratio test to the sum of the absolute values. I'm using it to analyze absolute convergence. Okay, well, what's this limit? Well, I can simplify this limit a bit. I could write this as the limit n goes to infinity. Let me pull off the c sub n plus 1 and the c sub n. It'll be the fraction c sub n plus 1 over c sub n. And then here I've got n plus 1 copies of x minus a. Here I've got n copies of x minus a. Most of those will cancel. All that I'm left with is just one copy of x minus a in the numerator. So I'll write times absolute value x minus a. And the ratio test tells me that if this is less than 1, then the original series converges absolutely. And if this is bigger than 1, then the original series diverges. Well, how can I really analyze this? I mean, I don't really know anything about c sub n plus 1 and c sub n, but let's just pretend, right? Let's just pretend that the limit just of the c sub n plus 1 over c sub n ends up being 1 over r. And in this part here, the absolute value of x minus a, that's just a constant anyway, so I'll write times absolute value x minus a. And I'm wondering, when is that less than 1? Well, I mean, I'm just playing make-believe here. R is some positive number. I'll multiply both sides of this inequality by r. Since it's positive, it doesn't affect the inequality at all. Now I've got that absolute value x minus a is less than r after multiplying through by r. Well, what does this mean? This means the distance between x and a is less than r. Well, that really means that x is between a minus r and a plus r, and that at least when x is between a minus r and a plus r, I know that the series converges absolutely. I don't know what happens at the endpoints, but the big deal here is that, look, this thing legitimately looks like an interval centered at the point A with radius r. In what's to come, I'll usually be talking about power series that are centered around zero. But it's important to realize that we can talk about power series that are centered around some other point. And there's certainly cases where that'll come in handy.